Hello class, in this video we cover the concept of probability, section 11.4. We are going to introduce two types of probabilities, okay? Theoretical probability and empirical probability. In fact, besides those two types of probabilities, we have another subjective probability, but we do not cover subjective probability. In this section, we only focus on theoretical probability and empirical probability. So let's start from the theoretical probability model. Okay, let's start from theoretical probability model. Theoretical probability is also called a classical probability. Let's introduce some simple basic definitions. Let's start from experiment. And let's think about this example, okay? Let's think about rolling a dice. The 6-size cube. You can see that everywhere in casino. Rolling a dice. Let's consider this example. Or die. Yeah, rolling a die. Dice is maybe plural. Yeah. So experiment is any occurrence for which an outcome is uncertain. So rolling a die is an experiment because before you roll the die, you would not know what outcome will occur, right? You would not know if you get a 1 or 2 or 3 or 4 or 5, 6. So rolling a die is an experiment. Same with toss a coin, right? And deal a card from the standard deck of cards. So those are experiments. Second concept, outcome. Outcome is a result of an experiment. A result of an experiment is called outcome. So in our example, rolling a die, we have 6 outcomes, okay? We have 6 outcomes. And each outcome cannot be divided into even smaller parts, no. So you can get a number 1 or 2 or 3 or 4 or 5 or 6. And we have 6 outcomes from this experiment. Sample space. Sample space corresponds to experiment. So when we talk about sample space, we should actually specify sample space of which experiment. Sample space of an experiment is a set. The set contains all the possible outcomes of that experiment. And we use the capital letter S to represent sample space. In our example, rolling a die, all the possible 6 outcomes are 1, 2, 3, 4, 5, 6, right? So the sample space would be a set containing all the 6 possible outcomes. 1, 2, 3, 4, 5, 6, right? Sample space of this experiment. If we roll a die and observe the resulting number, and that is an experiment, and the sample space of that experiment is a set containing those 6 outcomes. Next concept, event. Event is any collection of 1 or more outcomes, denoted with capital letter E. Other books use capital letters A, B, C more often. So our book uses E because E is the initial of event. An event is any subset of the sample space. Let me give you the examples. Let's say I use A, B, C, D, okay? Let's consider event A. rolling a die and get a number 6. Then I can describe the event as a subset of the sample space, right? Yeah, containing one element. And if I consider event B, why is it blue? So if I consider event B, what is event B? We roll a die and we got an even number, even. We know what is even number, what is odd number, right? Then we can describe the event B also as a subset of the sample space. Any collection or any subset of the sample space can be seen as an event. So event B, we roll a die, we get an even number, could be described as a subset of sample space containing 2, 4, 6. When you roll the number 2, it's an even number. When you roll the number 4 or number 6, they are all even number. So that they all contribute the event B occurred. So those are 2 examples of events of an experiment. But those 2 events are different. Event A actually is an outcome as well. Yeah, event A is an outcome. But event B is not an outcome. Do you see the difference between outcome and event? So those are basic concepts. And now please take notes. And those notes are not included in the guided note. So a theoretical model. Sorry, I wanted capital A. A theoretical probability model, also called a classical probability model. Refers to an experiment that satisfy the following conditions. The first condition, the sample space of the experiment contains finite number of outcomes. Only finite numbers. Number 2, the finite number of outcomes in the sample space are equally likely to occur. You see the symmetry in those outcomes. Contains a finite number of outcomes. Condition number 2, the finite number of outcomes, they are equally likely to occur. So if those 2 conditions are satisfied, then the experiment is a classical model or theoretical model. All right? Yeah. So please include that in your notes. Let me highlight in bold and red. Our example, rolling a die, is a classical model. Why? Because it satisfies the conditions in the description. The sample space of rolling a die, the experiment rolling a die and observe the number, has a sample space 1, 2, 3, 5, 6, right? Yeah, that is a finite number, only 6 outcomes. And all the 6 outcomes are equally likely to occur if the die is fair, F-A-I-R. Nobody is cheating. All the 6 sides have the same weight. Then you would have the same chance to get a number 1, number 2, number 3, number 4, number 5, number 6, right? Yeah. So that is a classical or theoretical probability model. Very important concept. Yeah, it's not in the guided note, so please include it in your note. I can give you other example. For example, toss a coin. Toss a coin is an experiment because before you toss the coin, you would not know, are you going to get a head or are you going to get a tail? But you know you are going to get only two finite number, right? Only two outcomes, tail and head. And the tail and head, those two outcomes are equally likely to occur. If the coin is fire, then tossing a coin is also a classical model. Classical model. And all other, do we have any other examples? For example, if we consider rolling two dice, okay? We can consider a red die and a green die, or die number 1 or die number 2. So is this plural also die? Dice, okay, yeah, dice, plural is dice, rolling two dice. And consider the sample space of this experiment. How do we record the outcome? Since we have two dice, then we're going to have two numbers, right? One number from the first die, the second number from the second die. So one way to record the outcome is to use an ordered pair. 1, 1 represent the first number. The number from the first die is 1. The number from the second number is 1 as well. Second die is also 1. And 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. And 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Sorry, it's going to take a little bit while. Let me finish. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Oops, 4, 6. And 5, 1, 5, 2, 5, 3, and last row 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. That's the sample space of the experiment of rolling two dice, right? How many outcomes? 36, finite number. And all those 36 outcomes are equally likely to occur. They have the same chance to occur. Suppose the two dice are fire dice. Okay, so that is a classical model as well. Yeah, so those concepts are important, but more important is you know what is a theoretical probability model. The sample space must contain finite number of outcomes, and all those finite number of outcomes are equally likely to occur. That gives us a theoretical classical model. If we have a theoretical probability model, then this is how do we find the probability. Let me give you the formula. This is how do we find the probability in a theoretical probability model. In other words, this formula is how do we compute the value of the theoretical probability of an event. Okay, yeah, we use this notation P of A to represent the probability of A, P of E to represent the probability of E. Knowing that for any events, the probability of the event must be between 0 and 1. The probability of any event must be bigger than or equal to 0 and less than or equal to 1. When the probability of the event equals 0, the event is impossible. When the probability of an event is 100%, right? Then the event is certain to occur. We'll see examples of those two special cases. It's a very straightforward concept. Let's look at the formula though. This is my formula. I use P of A equals K over N is a fraction. Okay, the numerator always less than or equal to the denominator. To guarantee the fraction is between 0 and 1. No less than 0, always be non-negative and no bigger than 1, no bigger than 1. At most 1 when the event is certain to occur. And the denominator n is the number of outcomes in the sample space. Yeah, again, we are talking about a theoretical probability model. If we have a theoretical probability model, that's the formula we need to apply to compute the probability of an event. Denominator, yeah, to find the event, to find the probability of the event, find the two numbers, a denominator and a numerator. The denominator is the number of outcomes, different outcomes in the sample space. Numerator is the number of outcomes favoring event A. Okay, for example, we roll a die, right? Yeah, how do we find the probability of A here? We already agree rolling a die is a classical model, theoretical model. And to find the probability, we use a fraction, denominator and numerator, right? Denominator is 6 because we have 6 outcomes in the sample space. And numerator is what? Is 1 because event A only has 1 outcome favoring the event. And how do we find the probability of B? Denominator is the same, right? It's the same theoretical probability model. And numerator, how many outcomes in event B favor the event B occurring? We have 3. So that's how do we have 1 over 2 if we simplify the fraction. That's the probability, right? And another example, if we consider rolling 2 die, 2 fire die, and how do we find the probability of event E? What is event E? Getting 2 numbers, roll 2 die, and the sum of the number equals to 4. How about that? All right, so how do we find the probability of E? P of E is going to be a fraction. Denominator on the bottom, numerator on the top. Denominator 36 because we have 36 outcomes in the sample space for the event, right? And numerator, let's look at the 36 outcomes. How many of them favor the event E occurring? How many of them favor the sum of the two numbers equals to 4? 3 of them, okay? So the numerator is 3. And you simplify this fraction, 3 over 36, 1 over 12. And the interesting thing I want to show you is this would be useful for you when you work on the homework in math. This event, this outcome, the sum of the two numbers is 2. All right, you see the pattern. And those two outcomes, sum of the two numbers is 3. And those 3 outcomes, sum of the two numbers is 4. And the sum of two numbers is 5, 6, 7, 8, 9, 10. Oh my gosh. So here, sorry, I missed this one. 7, 8, 9, 10. Yeah, 10, 1, 2, 3. 3 outcomes have the sum of the two numbers equal to 10. And 2 of them, sum is 11. 1 of them, sum is 12. Do you see the pattern? All right. So that's how do we find the theoretical probability for an event in a theoretical probability model. Just to find the numerator and the denominator. Let's apply. This problem is about dealing cards from a standard 52 card deck. Some students would say, I never play poker. I do not know what's in a standard 52 card deck. You know, in order to do the homework and the test, prepare for the test, you will have to spend time and effort to get familiar with what's in a deck of cards. In a deck of cards, we have 4 suits. We have 52 cards in a standard deck. And among the 52 cards, we have 4 suits. Yeah, we divide the 52 cards into 4 suits. hearts, clubs, diamonds, and spades. What do hearts look like? The hearts cards look like. They have a red heart there. So that's hearts. Clubs look like that. It's black. Diamonds look like that. It's red. And spades looks like a black heart with a stick, right? Stem. Yeah. So you're gonna spend time to get familiar with those information. Some of you, I bet you are very familiar with those things, but some of them might never play poker. But for the purpose of dealing with the class, you would have to get familiar with the content. Each suit, we have 13 cards. A here is represent number 1, and number 2, 3, 4, 5, 6, 7, 8, 9, 10. J here is 11. Q is 12. K is 13. All right, so 13 times 4, 52. So we have 52 cards in a deck. J is jacks, Q is queens, K is kings. And let's see, how do we process this example? You are dealt one card from a standard 52 card deck. Find the probability of being dealt a jack. So randomly select a card from the deck. That's our experiment, right? Yeah. Apply conditions to determine if the experiment is a theoretical model. It is a theoretical model because we only have 52 outcomes, and all the 52 outcomes are equally likely to occur. All the 52 cards have the same chance for you to select. And what's the probability of select a card and the card is a jack? So we have 52 cards, right? And how many of them are jack? 4 of them. So 1 over 13. The probability is 1 over 13. And you know, we have another way to compute the probability of randomly dealing a card and the card is a jack. And this is very important. Please pay attention. Yeah, we could change the way we look at this experiment. The experiment could be dealing a card and write down the number, right? Or could be dealing a card and write down all the detailed information of the card. So if we only consider the number, yeah, if we only consider the experiment, get a card, pick a card, and record a number. It doesn't matter is a heart or club or diamond or spade. Then the sample space only has how many 11, 12, 13. How many outcomes? 13 outcomes, right? And all the 13 outcomes are equally likely to occur because every number card has 4 cards. 4 cards are A, 4 cards are 2, 4 cards are 3, and so on, right? With that said, the denominator is 13, and a jack 11 is 1, so 1 over 13. Do you see what I'm talking about? Yeah, so smartly select your sample space sometimes makes your job easier. Part B, a card greater than 3 and less than 7. So we consider the same sample space. Yeah, the experiment would be pick a card and write down the number. Then the event getting a card that is bigger than 3 and less than 7, the probability would be, what is it? Denominator is 13 again, right? And numerator, how many of those 13 outcomes favor this result or event? Bigger than or equal to 3. Sorry, my bad. Bigger than 3 and less than 7. So bigger than 3 does not include the 3. So start from 4, 4, 5, 6, and strictly less than 7, right? So only 3. 3 over 13. Only 3 outcomes favor the event. Yeah, bigger than 3, less than 7. Do not include the 3, do not include the 7. So 3 over 13. Part C, the ace of clubs. Since this event specify what suit of the card, then this sample space doesn't work anymore, okay? And now we would have to consider the sample space as a set containing all the 52 different cards. In that case, the denominator would be 52. And how many of those 52 cards are ace of clubs? Ace of clubs. We only have one ace of clubs, right? So 1 over 52. Part D, a card with a green heart. Okay, so we consider all the 52 cards. Any of them has a green heart? 0. So the probability of getting a green heart card is 0. Yeah, that event is not possible, is impossible. Number 2, use the spinner shown to answer the following problems. Assume that it is equally probable that the pointer will land on any one of the 10 colored regions. So we have 10 regions. 10 regions. And as you can see, those 10 regions have the same area, right? Same area. That means the chance to get each region is the same. If the pointer lands on a borderline, spin again. Yeah, that's what's going on in this situation, in this experiment. We are going to find the probability for the following events, 4 parts. Part A, a yellow region. Yeah, what's the probability when you spin the spinner? What's the probability that you get a yellow? A common mistake, let me tell you, the common mistake is to consider sample space as a color region. But there's a problem of doing that, because if we consider colors, we have yellow, brown, blue, red. 4 colors, right? However, those 4 colors are not equally likely to occur, because as you can see, you have 3 red, 2 blue, 2 yellow, 3 brown. They do not have the same chance to occur. So you are not considering, you do not have a classical or theoretical model. So you cannot use that as a sample space. You would have to use the 10 regions as the sample space, okay? Because the 10 regions have the same area and they are equally likely to occur. And you have a classical theoretical model by using that sample space. And what's the probability of getting a yellow region? So the denominator would be 10, right? Among the 10 regions, how many of them are yellow? 2. So the probability is 1/5, 20%. Part B, what's the probability of getting a brown region? Among the 10 regions, how many of them are brown? 3. So 30%, right? Yeah, 0.3 doesn't matter how do you enter the, it matters, depends on how the question requires you to enter the answer in what certain format. Part C, a region that is yellow or brown. Denominator still 10, right? Yellow or brown. Yellow or brown. So 2 yellow, 3 brown. So yellow or brown, 5. You have a 50% chance, 50% chance to get a yellow or brown. Part D, a region that is yellow and brown. So among the 10 regions, do we have a region that is yellow and brown? No, so 0. That event is impossible, right? So that is classical or theoretical probability model and the formula to compute the theoretical probability in the model. So as I mentioned earlier, we only talk about 2 types of probabilities, theoretical and empirical. If a model is not classical or theoretical, then the model must be empirical. So let me give you an example about the empirical. Let's say you're going to do a survey. Empirical actually is more popular in reality. When you do your research, if you are a social science major and you need to do some research, right? Let's say you need to survey for the purpose of getting the statistics and the percentage of people who smoke in Tulsa area, right? So you are going to survey 1,000 people, randomly select 1,000 participants, okay, or participants or subjects, and among the 1,000 people you survey, you ask question: are you a smoker or are you not a smoker? 200 of them are smokers, and the other 800 are not smokers, non-smokers. So you are going to find the probability of randomly select a person in Tulsa area and the person is a smoker. Think about this experiment. Yeah, consider this experiment. Randomly select a person in Tulsa area and record if the person is a smoker or non-smoker. How many outcomes in your sample space? 2 outcomes in your sample space, right? Yeah, the first outcome, smoker. Second outcome, non-smoker. However, this model is not a theoretical model because getting a smoker and getting a non-smoker are not equally likely to occur. They are not equally probable. So this is not theoretical. It has to be empirical. It has to be empirical because your goal is to find the probability of randomly select the person in Tulsa area to see if the person smoker or non-smoker, right? So your population, your concern, your population is the whole, all the people in Tulsa area, but you can only survey 1,000 people because sometimes we have to just get a sample to refer to estimate the result about the population. Yeah, later we're gonna talk about the relationship between sample and the population. So 200 over 1,000, 1/5 or 0.2. What is that? 20%. That is the sample proportion, okay? Yeah, you get a sample proportion. We can only say if your survey is representative, if your sample is representative, the sample proportion would be quite close to the population proportion. And the population proportion would be able to represent the probability of randomly selecting a person in Tulsa area and that person is a smoker. Yes, a little bit complicated. Or make it simple. If the model is not theoretical, you're going to know it's empirical. Then how do we find the empirical probability? Actually, in the empirical situation, it's not possible to find the exact value of the probability. We could only estimate. We could only estimate. We could only, the estimation is based on the law of large numbers. Yeah, law of large numbers. It states that as an experiment is repeated more and more times, the empirical probability of an event tends to get closer to the actual probability of that event. An analogy is, let's say you have a table. You want to know the actual length of the table. Are you able to know the actual length of the table? You can't. You can't. Yeah, the actual length of the table is a property of the table. That's true. But the actual value is not possible to acquire. We could only estimate. How do we estimate? We measure. We measure 1 time, 2 times, 3 times, and then we take an average of those measurements, right? And when the number of measurements is getting bigger and bigger, then the average would get closer to the actual length of the table. It's the same idea. we are using the proportion, sample proportion to estimate the empirical probability. Okay, make it simple. In a empirical probability model, what's the formula to find the value of the probability? P of A equals K over N. I use the same formula, but different meaning, okay? Different meaning. And denominator is the total number of observed occurrences. You survey 1,000 people, then the denominator is going to be 1,000. And numerator is the number of observed number of times the event actually occurs. Among the 1,000 subjects, you have 200 smokers, then numerator is going to be 200. Basically, you are looking for a frequency. Does that make sense? You are looking for a relative frequency. Relative frequency. So let's look at the example. When you work on MATH, you will see many problems to find the probability, but the given information is included in a table, then probably that probability is empirical. Yeah, as you can see here, you survey those people, the chance of getting a male and the chance of getting female not equally likely. And the chance you get people ages from 15 to 24 would not be the same with the chance of you getting other age groups, right? Yeah, it's not uniformly distributed. It's normally in general is probably normally distributed. So when you see a table and you need to find the probability, then it's gonna be empirical. Let's see, how do we find the empirical probability, right? So we are going to find part A is to find the probability of randomly select the American living alone is a female. Okay, so we only consider female gender. So the table gives us the number of people in the United States living alone in millions. Okay, so as you can see in the last column, how many people in total we have surveyed? 29.3 million, right? Yeah, let's just ignore million. Among those 29.3 million subjects, how many of them are female? 16.8, right? And that's gonna be the numerator. That's it. It's pretty straightforward. Denominator is the total number of observed occurrences. You surveyed 29.3 million people, then the denominator is going to be 29.3 million. And numerator is going to be the observed number of times E occurs. How many times female occurs? 16.8 million times, right? So numerator is 16.8. And how do we express the result? We're going to express the result as a decimal rounded to the nearest hundredth. So keep 2 decimal places. If we divide 16.8 by 29.3, we get a decimal and round it to the nearest hundredth. We would have 0.57, round it down, and that's it. Depends on how the problem instructs you to round the result. Part B. What's the probability of randomly select an American living alone and the person is in the 35 to 44 age range? Denominator remains the same, okay? And among those people, how many of them are in the 35 to 44 range? 4.2, right? Okay, let's divide and round. 4.2 divided by 29.3 is around equal to 0.14. How do you understand the result? Among those people surveyed, around 57%. Around 57% are female, right? Yeah, more female living alone. And among the surveyed people, they live alone in the United States. Around 14% of them are, 35 to 44. Part C, a man in the 45 to 64 age range. So denominator remains the same. Numerator, among the 29.3 million people, how many of them are male and in the 54 to 44, in the 45 to 64 age range? Yeah, let's do this. Male, so this row, and 45 to 64 range. Do you see the first row and that column? They intersect which area, which region? They intersected here, right? So among 29.3 million people, there are 4.3 million people are male and ages from 45 to 64. So the numerator is going to be 4.3. Let's see the result. 4.3 divided by 29.3 is around equal to 15%. 0.15, round it up. All right, so that's empirical model. I believe you can understand this. If you understand the table, you should be able to compute empirical probabilities. The last part of the guided notes is about how do the empirical probability tends to get closer to the theoretical probability if the number of experiments approaches infinity. As you can see the result here. If you only toss the coin for 10 times and you get 4 times of them as heads, then the empirical probability actually is a frequency, right? Relative frequency is 40%. But if you raise the number of tosses to 50, and you get 54%, 144%. It varies. 1,000, 53%. 10,000, 48.51%. 100,000, 49.88%. If you have a computer, you can generate the result very well. You can let n, the number of experiments, the number of tosses, approaches to infinity. You will see the empirical probability will tend to approaches to 50% or 0.5. One more thing I want to point out is not every event has a theoretical model, a theoretical probability value. This is actually a theoretical model, as you can see. Toss a coin. But many other situations, they are not theoretical. So it's not possible for us to find the exact value of the probability. We could only estimate. We could only use the sample proportion to estimate the empirical probability. That's everything for today. 2 types of probabilities. Focus is to identify theoretical probability model and how do we compute the theoretical probability by using the formula, numerator, denominator. If the model is not theoretical, then it's going to be empirical. Then in empirical model, how do we find the denominator and the numerator to estimate the empirical probability? Okay, so if you have any questions, feel free to email me. I'll see you in the next video.